Jesse, and today we're introducing your practical material relating to the distribution of variables and how to transform and standardize them.
So this is a brief chat about the Week 4 prac, a workshop class for ENVT3361 on looking at the distribution of variables and transforming them if necessary. If you want to have a look at this in more detail, the textbook by Riemann et al. Is really good, especially chapter 10, specifically on transformations, and of course it's available for you guys for free as an ebook on LMS. Okay, so in the real world, our variables, such as exchangeable magnesium in the Hubbard dataset, are not normally distributed, not without transformation. We can assess this using a histogram where we can see a skewed distribution with a tail towards high concentrations, and also in the QQ plot where our data are not linear or not along the ideal normal distribution line of the QQ plot, nor are they within the 95% confidence intervals. And again, that deviation is seen at high values of exchangeable magnesium corresponding to this tail on the histogram. So we can run those graphs as a graphical analysis of distributions in R using the CAR package, of course, for the QQ plot. Okay. Why do we do it? Well, partly for graphical analysis, or for example, scatter plots and things, we don't want all the points bunched along an axis, so we transform the data to spread them across a reasonable range. But more importantly, many of our traditional statistical methods require or assume our data variables to be normally distributed. That includes things like t-tests, ANOVA, correlation, regression, and so on. And the other reason we do it is to normalize the variances, to equalize the variances, between groups. That is to create homoscedastic from heteroscedastic data. And ANOVA and regression, for example, also assume that, and we can violate those assumptions if our data are not transformed. And there are some specific issues to do with multivariate analysis, which we won't go into in this unit. Typically, we restrict ourselves, and this is what we'll do for our assignment, to restrict ourselves to a couple of types of transformation. We're mostly dealing with measurements, and so we tend to use log transformation, which suggests that log 10 is going to be the best option for us because it's a bit more intuitive, or we use power functions, raising our variable to the power of some number. It's hard to know what that number should be, but fortunately there's an algorithm to find out the power transform function within R. If we pop our variable and run it through that algorithm, it'll give us a value of a power transform. So it won't necessarily come up with minus 0.5, for instance. It may come up with plus 0.2 or something like that, but you'll get a number which is the best possible power term to use in our power function using the power transform. There are some specific things that we need to be careful of if the estimated value turns out to be negative. For different types of information, we use different transformations, but just bear those in mind for now. Do you need to transform your data? Well, first of all, we can look at what statistical tests we want to use. And as I said, most of our traditional statistical methods do require normal homoscedastic data. We don't necessarily need to standardize. That's transformed to the mean and standard deviation of the standard normal distribution. So we can do it graphically, but one thing we also should do is apply a null hypothesis significance test, and that's the Shapiro-Wilk test, which will compare the distribution of our variable with that of a standard normal distribution having the same mean and variance. And if we run our variable through the Shapiro test without transformation, we can see it has a p-value of less than 0.05, which means that we reject our null hypothesis that our distribution is the same as normal. We actually want to be able to not reject our null hypothesis that the variable distribution is the same as a normal distribution. So to pass the Shapiro-Wilk test, p-values would need to be above 0.05. That is, we can't reject the null hypothesis. So here's an example of that using power transformation. Ignore these two speech bubbles here because they relate to the R commander package. However, the middle speech bubble is important. So if we run the power transform function on exchangeable magnesium, it calculates the best power term to use. So we need to raise exchangeable magnesium to that power every observation to create a distribution that's close as possible to normal. So we do that. Here's a new variable, and we use with, which is, I'll talk about in a minute. You don't have to do it this way. There are other syntaxes that we can use. And we raise exchangeable magnesium to the power of our power term here from the power transform function. Notice that the power transform is calculated a negative number, and so we multiply the whole thing by -1 because the negative number will reverse the ranking or order of our data. We want to reverse it back using the factor of -1. Then we can, with our new variable, run the Shapiro test again. Now it has a p-value of 0.7. We can't reject the null hypothesis, which is good in this case because it means that our distribution, as we can see in the histogram here, not significantly different from normal, and that's confirmed by the QQ plot. Okay, so just a point about the with syntax. These two lines are equivalent. So on the left-hand side, it's the same. We've got the -1 times exchangeable magnesium to the negative power here, but we're specifying the data object differently using a with statement. Remember that it's exactly the same as specifying the data object using the dollar syntax as well. So they do the same thing. All right. Similarly with a log transform, log transformation is a bit easier to run, so just log10 variable name, and then we retest the log transform variable. Notice that the p-value allows us not to reject the null hypothesis, so our distribution again not significantly different from normal, which is good. It's a pass. Histogram shows that graphically, as again does the QQ plot. So just putting all that together, we had a variable, and you'll have many variables to test, which had a skewed distribution, so a high tail in this case, and it had a p-value below 0.05 on the Shapiro-Wilk test. Its distribution is different from normal. With transformation, and our most appropriate transformation is a log rather than power, just because it's easier to understand. Always use log in preference to a power transform if it passes the Shapiro-Wilk test. Okay, so we can see that the log transform gave us a p-value that allowed us to not reject the null hypothesis that our distribution now is not significantly different from normal. And you can take it a step further, but we don't need to do that. We can scale that to have a mean of 0, standard deviation of 1, and that's what the scale function within R does. Notice, though, that the Shapiro-Wilk statistics don't change as a result. And there's the actual normal distribution superimposed on that log transform variable, showing that they're actually not that different. Sometimes we have variables that you can't transform. For example, if we have significantly high outliers, in this example here, we can't do much about that. We can't do much about multimodal distributions, which might be the sum of two distributions of separate populations. Now we can make use of that. We'll come to that in another prac, but we can't transform that whole variable. Sometimes the shape is just wrong. Okay, we can't do much about that either. Okay, so sometimes we need to accept that no transformation will normalize the distribution because these are natural samples and they don't behave like we want them to. In that case, we use different types of statistical tests from the conventional ones. For example, Spearman correlations instead of the more commonly used Pearson, or Kruskal-Wallis tests of differences in means instead of ANOVA or a t-test or something like that. Okay, this is what you're going to do this week. This is all on LMS and has a due date towards the end of the month based on what you do in the workshop today. If you really want to automate the whole process of creating transform variables and testing them for normality, there's a script that will do it for you if you want to have a crack at that. It creates data that will be easy to copy and paste and make a CSV file from, so you can make tables and so on for reports. Okay, that's all we have there for you.